It is started.
It's my pleasure to introduce Dr. Sanjay again for his second lecture with us on statistical mechanics. And he has done his graduation and post-graduation from University of Delhi. His doctorate is from Purdue University. Not the slide, previous one, please. Purdue University, USA, and he has been very deeply involved with the students in the sense that what should be done for the students for their understanding, for the depth understanding of a particular subject for all subjects. And he has been deeply involved with the University of Delhi, reforming the syllabi, the course curriculum, the way the numericals are designed, and so on. And we are really grateful that because of his involvement, we have really a new change in our university where the students have started doing numericals at a very large scale from undergraduate level, first year itself. So welcome, Dr. Sanjay. Please continue.
Thank you, Dr. Verma. Thank you, Dr. Bindal, and a lot of thanks to Nasi for giving me this opportunity to present this lecture. And last but not the least, to all the participants who are here. So yesterday we had started with the certain basic concepts, and our idea is to go into the subtle points of those concepts, the points where confusion can arise. So yesterday we did two of the topics, namely microstate, macrostates, and phase space, which are important in representing or making a statistical description of the physical phenomena. And the second thing which we discussed was the idea of random fluctuations, which are part of all statistical systems, but a very important result as the number of particles or the constituents of a system increases. The maximum probability becomes the most likely state. In the other states are possible, but their probability becomes extremely small compared to the maximum probable states. And the key idea then is that we can associate the equilibrium states from thermodynamics. The idea of equilibrium states are the ones, these are the states which do not change with time. So then we can associate equilibrium states with the most probable states from the statistical description. So that was a very important conceptual association. Today we'll discuss the next other two topics, namely that statistical physics basis of thermodynamic properties. Yesterday, I just briefly mentioned that one should view statistical physics a kind of bridge. On one side are the basic constituents of these systems. There could be atoms, photons, molecules. And so these are constituents which follow the laws of microscopic physics, most often the quantum physics laws, or one can also assume them to be following the classical physics laws in certain limitations. So on the one side, we have these micro constituents of the systems, and on the other side is the thermodynamic description, which deals with the overall properties of the system. And statistical mechanics established between it's a bridge, and it's nature. That's why we're calling it statistical physics, because it deals with the probabilities of random phenomena. So what we'll do to passage from microscopic description in terms of microstates to a thermodynamic description. Okay? And you will see how the relationship like entropy is equal to k log times the number of microstate arises. And then we'll also discuss a very important concept in statistical physics, namely partition function, which if you know partition function of any physical system, then practically you know everything of relevance as far as statistical physics is concerned. So partition function calculation remains a prime problem in all statistical physics problems, and we'll spend some time at least doing one example in detail of how to find partition function. So today we'll deal with these two things. Okay? So let me jump over a lot of slides. These slides were discussed yesterday, so we won't go over them again. Now we are going to go to further down. This is still the fluctuations part. Okay, so this is the statistical basis of thermodynamic properties. So let's imagine we have two systems, okay, and which you're calling them system A1 and system A2. The number of microstates of the system one is just some omega 1 and other is some omega 2. Okay. Microstates basically means a complete description of the state of constituents of the system. And here omega 1 is the number of such microstates. For instance, if it is a volume of gas, then the position and momentum of all the molecules would constitute a microstate, and the number of such microstates consistent with the overall property of the system. For instance, the system could have some finite volume, it could have some energy, it could have some pressure. So depending upon all those external constraints, there would be a specific number of microstates available to it. Okay. And system 2 similarly has omega 2 number of microstates. Okay. Now what we've done here in this diagram is we have allowed this system to interact with each other, and this boundary is a thermal boundary, meaning it allows energy exchange between the two systems. But that's it, only energy exchange, nothing else. Okay. So this is a kind of thermal boundary. Okay. Now, naturally, when we allow energy exchanges between the two systems, energy of this is no longer constant, and similarly here, but whatever energy is lost by this is gained by this. And remember, this energy exchange is a random process. So energy of both these constituents will be fluctuating. But what we know is that if you take the total system made up of both of them together, remember, the system is just a system. You can look at these subsystems separately. You can look at the two of them together as one system. So E0 stands for the energy of the system as such. And the system made up of these two is isolated. So the sum of the energy of E1 and E2 at any moment is constant. And that is the energy of the total system. And here is the idea that these systems are constrained, that energy gained by one of them is coming from energy loss for the other. So change in one of them, change in energy of one of them is opposite to the change in energy of the second one. Okay? So that's a constraint on changes in the energy. Okay? Now we come to this very important equation. Now what it is saying is, okay, omega 1, the number of microstates. There could be other quantities, but here we are looking at only the dependence of the number of microstates of the first system on its energy. Okay? So omega 1 is a function of the energy of the first system. Omega 2 is a function of the energy of the second system. So that's there. On this side, we have the number of microstates of the combined system, which you are indicating with this superscript 0. Now, this is the crucial equation, and from this, everything else follows. Okay? So what you're doing here, it's the important thing is just when you microstates is a matter of counting. So if you have one microstate for omega 1, corresponding to that you will have omega 2 microstates. So if you want to talk about the number of microstates of the total system, that will be the product of the microstates of the two systems. It's not sum. Mathematically, it's a product. And this point that it's a product function is very, very important. And this product function basically comes how you count. So this is the microstates of the total system written, which is the product of the microstates of the two subsystems. Now we have written down it as the function of E1 and remember the constraint is that E1 and the sum of the E1 and E2 is constant. So we can actually eliminate one of them. So let's eliminate E2. So then this becomes a function of E0 and E1, but E0 is constant. So any change in omega 0 you can represent in terms of change in E1. That's how we incorporated the relationship between E1 and E2. Now let's proceed and see what we can do. We get to this very, very important result. What is an equilibrium state of a macroscopic system? Equilibrium state of a macroscopic system is a state with the maximum probability. And the state with the maximum probability is the one which has the largest number of accessible microstates. Okay. All right. So that is the basic idea which you are borrowing from the yesterday's lecture. So we want to understand what happens at the state of equilibrium, and the way to get is to get the state which has maximum probability, which means the state which has maximum number of accessible microstates to it. We know that the two systems, the number of microstates is omega 0, and we want to find out the energy at which that omega 0 becomes maximum. Okay, so what we need to do, find out what is the consequence of partial derivative omega 0 with E1. Remember earlier we had shown that we can eliminate E2 and only one of the energies is relevant because E1 plus E2 is constant. So if there's a change in E1, okay, that's a partial derivative. But to get the maximum value of omega 0, we put it equal to 0. So I will put off the video here. So if there is a, because there could be a problem with the bandwidth. Okay, so we have an expression for omega 0 and write it like this. So this is the partial derivative of E1 and E2. Here we are just writing it as second because omega 2 actually is a function of E2, but E1 and E2 are functions of each other, so they are related. Their changes are related, so we also use the partial. We are writing E2 as a function of E1 in this expression. Okay, but delta E2 by delta E1 is simply -1. Okay? So we can write this expression. So this term gives you -1. You take it on the other side, you get this. Now, what is the physical interpretation of the system? These are on both the sides functions. They are basically functions of the microstates, or what you can say functions of the statistical physics description of the phenomena or the system. The number of microstates, how that changes with energy, divided by the number of microstates. And what you're saying is that at equilibrium between the two systems, okay, when you say, okay, the system has reached equilibrium, remember when even it is at equilibrium, there will be fluctuations, as we discussed yesterday. So this is not the thermodynamic equilibrium that everything is stationary, nothing is changing. No longer that's the case in statistical physics. There will be fluctuations all the time. So the idea here is that at equilibrium, there is a property of the system which is given by this expression. And for systems which are in thermal contact, this property of the system is same for both of them. Okay? And if you remember, the derivation of temperature in before the zeroth law of thermodynamics, something happens there. Okay, so we have two systems in thermal equilibrium. They have the same value of this function of the microstates. This microstate is a function. All right. And what is the physical quantity which you say is equal when two systems are in thermal equilibrium? In thermodynamics, you call that quantity as temperature. We say at thermal equilibrium, two system property, and that property is called temperature. Okay, so similar thing is going to happen here. And we put that this function same for both sides. And at the moment, see, we still have not gotten, we have not used the word temperature at all. So let's not use the word temperature at all. That will come in the next step. But all you're saying is that there is some property of the system, let's call it beta, we're just giving it a name, which is equal to this partial. When a system is in thermal contact with another system, then both the systems have same value of this quantity. So this is how far we can proceed from following from the just the statistical physics interpretation. Now what we do is we go to thermodynamic relationship. Okay? And in thermodynamics, this is a relationship which can be derived from Maxwell's relationship, but it tells you the following, that if you take the partial derivative of entropy with internal energy, then that is equal to 1 by T. This is the thermodynamic relation. This is not statistical relation. We're going to compare this relation with what you had earlier. Okay. So thermodynamic integration would be delta S by delta E for two systems should be same. Okay, because that is equal to inverse of the temperature, and the two systems have the same temperature. We have similar statement here. These two statistical functions of the system should be same when two systems are in thermal equilibrium. Physical situation is same. Okay, we have two systems in thermal equilibrium. We're describing the same physical situation in two different languages. In the language of statistical physics, you're talking about microstates. In the language of thermodynamics, you're talking about entropy. All right. So these are two relations, and we just compare with another, and through comparison, we establish the bridge between the two. So what here corresponds to what there? That is the bridge we're talking about, and that relationship is the following. So we can define the beta in the earlier equation as 1 by kt, which is taking as a constant. Okay, we could absorb k somewhere else also, but that's a convention. So beta is 1 by kt, and entropy is xk. So if you make that association of a thermodynamic function, namely entropy, with a statistical physics function, then this expression and the expression which you derive, they are describing the same physical state, but in different languages. Okay? So this is an example of how you create a relationship between statistical properties of the system and thermodynamic properties of the system. Okay? This is just one example, and we can go through the first chapter of Patharia. He discusses, how other properties of thermodynamic system ought to be expressed in terms of the statistical properties of the system. So we have made these two things. Beta, remember, is this quantity. This whole is beta, the partial derivative of log of capital omega by E. Okay, that's one thing. And then you compare it with the law of thermodynamics, which you got with this relationship thermodynamics, and figure out what can be entropy to make the two consistent with each other. Okay. Now, spend some time, because a lot of things depends. Spend some time in reflecting, why did you get the log of omega here? What is the origin of the log of omega? Because that's then, this log remains throughout in statistical physics. You will find this log function appearing again and again, and its inverse exponential function also appearing again and again. Okay? The source of that is this, that when you begin to talk about the microstates of a combined system, that is the product of subsystems. Okay? So log function essentially is coming from this statement. So log function is not something which appearing magically. A very simple idea of counting the microstates leads automatically to the log expression of log function in final functional forms. So sk log omega, why entropy is log function of number of microstates? Because of that multiplication factor there. All right, so we have established these relationships. Now let's try to reflect upon what these relationships are telling us. See, look at this relationship. S by the partial derivative of entropy with the energy is 1 by T. So naturally, as long as this partial derivative is positive, temperature is positive. And in thermodynamics, we almost assumed, well, this would be positive, because we thought, what's the point of temperature being negative? But notice, if you interpret S as k log of number of microstates, now we can begin to talk about entropy in something else. Entropy not as something given to us, but entropy in terms of number of microstates. Okay. Then it is possible to imagine systems, and there are physical systems also which are present, for which this partial derivative would not be positive. Okay, for which the number of microstates will decrease as you increase the energy. And we'll do some examples of that. Okay? So statistical physics then is telling us something very important. If there are systems which have an upper bound on energy, then it is possible that for these systems, there could be some domains for which the number of microstates decreases with increase in energy. Then you get something very, very counterintuitive. For such states, temperature would be negative. Okay, very, very important and interesting result. All right, so keep this in mind because we'll be doing an exercise with this later. Okay, this is now an exercise in which some of the ideas we had discussed earlier, they come to, we get to use them. Okay, so read this question carefully. Okay, we have a system of n number of distinct atoms, and can be very, very large. And all these atoms have discrete energy levels. Okay? And these energy levels are non-degenerates, meaning that at every energy level is a single state. Okay? And these energies of these levels are, 0, epsilon, 2 epsilon, 3 epsilon, etc. There's no upper bound on this. Okay? Now, there are different parts of the questions. Now, what is the entropy of the ground state of the system? Number one, what are the entropies when the system has energies epsilon and 2 epsilon? And what is the entropy when the system has energy E? And what is its temperature? So these are the 4 questions you have to deal with. Now let's see, deal with them. Okay, let's see first of them. What is the entropy of the system when the system is in ground state? Ground state means the system is in the lowest possible state of energy. Okay? And for this case, where the lowest possible energy of any atom is 0, so lower possible energy for the entire system would be 0. Okay? So that's a ground state. The system is in ground state with energy 0. That means all the atoms have energy 0. They are in an E equal to 0 energy state. How many microstates are these? There's only one microstate. All the atoms in having internal energy equal to 0, that constitutes just one microstate. Remember, a microstate is a description of the constituents of the system. And there's only one description here, namely all of them have energy 0. So if the number of microstates is 0, if that capital omega is 0 and S is k times log of omega, so naturally entropy is 0. Okay, so that tells you the entropy at the lowest energy state when the energy is 0. Now let's talk about the other case. Other case is that when the system has energy equal to epsilon. Now, how is it possible? Well, that means that only one atom can have energy epsilon. The rest of them have to be having energy 0. That's how the system will have energy epsilon. Okay? Now, how many microstates this has? Well, one microstate is that first atom has energy epsilon, all the rest have 0. Second microstate, second atom has energy epsilon, all the rest are 0. So naturally, the total number of accessible microstates, which are consistent with energy of the system being epsilon, is n number of microstates. Got it? So in this case, the entropy is Sk log n. The second case is when the total energy is 2 epsilon. energy of the system. Okay? Now, how can you have something like this? There are two possibilities, two sets of possibilities, not just two, in which you can have two system can have energy. One is that only one atom has energy 2 epsilon, rest are 0. Then we have the same situation as earlier for the energy being epsilon, that there will be n such microstates. So one state is one atom has 2 epsilon, all that has 0. Second microstate, second atom has 2 epsilon, all that has 0, and so on and so forth till the nth atom. That gives you n microstates. Okay? But the other possibility is that this 2 epsilon energy is divided with 2 atoms. One epsilon to one, other epsilon to other one, and rest of the atoms are 0. What number of states are in this case? Well, the number of microscales possible in this case is that you're picking up 2 atoms out of n atoms. Okay, so we'll have n factorial divided by, it will be nc2, so n factorial divided by n minus 2 factorial and 2 factorial. So that gives you this number, n into n minus 1 by 2. So the total number of microstates is now n plus n into n minus 1 by 2. You can add it up. So this entropy when a system has 2 microstates. And you can very easily see that entropy in the second system has more energy, is more than the energy in the first case where system had energy epsilon. So energy, the entropy is increasing as energy is increasing. So naturally temperature in this case will be positive. Now let's say in the general case, working with the same system, but now we say that system has some energy E. We'll leave this energy E undefined. Okay? But what we know is that this system has energy, it will be some multiple of epsilon, because energy states, they have values epsilon, 2 epsilon, etc. for each of the atoms, and total energy would be sum of the energy of the atoms. Okay? So what we do is you take, first of all, you find out this ratio, number which is E by epsilon equal to m. This is some number, okay? A natural number. Okay? Then what we can do is, this is a crucial step, and I guess you might have already seen it earlier. See, what we want to do is, so we can think of packets of energy. Okay, we have the packets of energy epsilon, and we say atom has energy, let's say 3 epsilon, and that atom has been given 3 packets of this energy. When some atom has energy 4 epsilon, that atom has been given 4 epsilon, 4 packets of this energy. When some atom is in the lowest energy state, 0 energy state, that atom doesn't have any packets. Okay. Now, what we want to now ask is, if there are n such atoms, in how many ways you can distribute m such packets of energy amongst these n of atoms. Okay. Now this is an exercise, you might already seen it. It can be done the following way. Okay, what we have done here is, you can imagine these boxes. Okay, so you imagine you're sitting on a table. So this is a kind of table, a flat surface, and you made a box for every atom. There are n such boxes. Okay. There are ends of the distribution. There can be one end here, one end here. That doesn't bother us. What is interesting to us is these separations, these things which separate the boxes. So this atom can have 2 packets of energy. This will have 1 packet of energy. This will have 3 packets of energy. This will have nothing, ground state. This will have 1. This will have none. So this is a possible distribution of a number of energy packets among a number of another number of atoms. Now suppose this is one state. Now suppose you want to find out another state. Another state could be that you can bring one atom from here to here. That will create a new state. Either you can imagine moving one atom to here to there, or imagine the following, that we have a system made up of these sticks, or you can say walls, okay, and these little spheres or balls. Okay. So we have number of balls is the number of packets, capital M, The number of separations or the boundaries separating different atoms is n minus 1. Okay, because the n boundaries don't play a role. Okay? So if you have boundaries between them, the n such atoms, okay, between them will have n minus 1 boundaries. So if you have this idea, n minus 1 boundaries and m number of energy packets, how you can distribute them among all the atoms. One way to look at it is that you can interchange, move around these balls and these boundaries amongst themselves. Okay? So instead of imagining, moving the ball here, you imagine this ball and this boundary can be interchanged. Okay. Then what we have m plus n minus 1 entities which can be interchanged among themselves. Okay. And how many ways you can do that interchange? That is m plus n minus 1 factorial. Okay. That's one thing. But the point is, if you interchange two boundaries, you don't get a new state. Because the state is basically how many energy packets in which atoms. Okay. So if you interchange this boundary with this boundary, this atom still remains one packet. You don't change that. Okay. So interchanging the boundaries does not create a new microstate. Interchanging balls does not create a new microstate. If you interchange this, bring this ball here, you bring this ball here, you still have one energy packet in this atom and 3 energy packets in this atom. So our earlier counting of interchanging all these sticks and balls, where number was m plus n minus 1 factorial, that is overcounting. We have to divide by the factors which basically, because interchanging sticks among themselves and balls among themselves does not lead to a new microstate. Okay? So then we have to divide it by n minus 1 factorial by m factorial. We can write down m as epsilon by e, and we get this expression. So we can write down omega in functions of e. Furthermore, since n is very large, you can even neglect 1 factor. So you get approximately an expression for the entropy of the system when not the entropy, but the number of microstates of the system and energy is E. You take the log of this, you multiply with K, get the entropy. And since these numbers you are saying n is large, epsilon could be also very large. So these are large numbers, factorials of large numbers. You can use Stirling's formula, and one can get an expression for entropy. So one can use, this is following the Stirling formula. Log of n is n log, and n factorial, log of n factorial is n log n minus n log n minus n. So you apply this for all these terms and you get this. Well, temperature, or the inverse of partial derivative of entropy is a function of S. So you get this expression. Okay, 1 at T is equal to this one, and work this out. Also, what is very interesting, we can invert this relationship. Okay? And that relationship tells you if the system is at temperature T, what is its energy? Okay, and let's be very clear. I have been. This is the energy, the mean energy. Remember, the energy would be fluctuating. Even equilibrium state would have slight fluctuations in the energy, and so this is the mean energy. Okay? So this is inversion of this relationship, that the mean energy of the total system when the system as at temperature T is this factor. You may already know, may have seen this expression coming from, Bose-Einstein statistics, and it is coming because we have talked about these energy packets being discrete. So same kind of argument leads to Bose-Einstein statistics also. But anyway, this was the example about this particular system. So we have used this example and learned how to find entropy for given concrete states. Okay. Now let's get to another very interesting example, which shows the concept of negative temperature. So now the model here is basically a large number of magnetic dipoles. Okay. And these magnetic dipoles can have only 2 directions. They can be oriented either along the magnetic, and there's an external magnetic field available. So system consists of this number of magnetic dipoles. These dipoles don't interact with each other, but they interact with an external magnetic field. And so there are two possibilities for every dipole. Either it can be aligned with the magnetic field or against the magnetic field. When it is aligned with the magnetic field, its energy is minus m times b, where m is its dipole moment, b is the strength of the external magnetic field. So when it is against the magnetic field, its energy is mb. When it is aligned with the magnetic field, its energy is minus m. So that's the situation. Oh, I think it should be, it's minus if along B.
Sanjay,
Okay,
along, if along,
should
I
not be
think.
against, it should be along B. Okay, there's a mistake here. Please.
Yeah, along.
Okay. So you need to derive energy as a function of entropy as a function of E and show that E is negative for, when E is greater than NE by 2. Okay. Now, before doing any calculation, what you already know about the system. Okay. What is the lowest energy state? Well, the lowest possible energy is when all these dipoles have energy minus mb. Okay. Then the lowest possible energy is minus n into m into b, or minus n times epsilon. Is there an upper bound on the system? Yes, there is an upper bound. And upper bound of the energy comes when all of the dipoles are against the magnetic field. Then all of them have energy epsilon. And at that point, the total maximum energy is n times epsilon. So energy can range between minus n epsilon to n epsilon. There's a lower bound as well as an upper bound. So that's something we already know about the system. Okay, now let's work out the number of microstates, etc., and find the entropy. So what you've done first of all is we're defining these quantities. N plus is the number of dipoles which have energy n, energy epsilon, n minus which have energy minus epsilon. The total of course, n plus and n minus should be equal to n, and energy can be written down as this factor, n plus minus n minus multiplied by epsilon. So these are basically coming from the definitions of n plus and n minus. Okay. We can write down n plus, then we can use these expressions to write down n plus in terms of the number of atoms or the systems, the dipoles, sorry, and the energy of the system. And we're doing it for a purpose because ultimately we want entropy as a function of energy. So we are writing n plus and n minus in terms of the energy of the system by these relationships. Now, how would you find the number of microstates? Well, the situation is pretty much like in the earlier case. We have total number of n dipole moments. Okay. And we say, out of this n, in how many ways they can be n plus dipole moments? In how many ways you can pick n plus? In how many ways you can pick up n plus? Okay. So that again is, n, c, n plus combination. So this is the n factorial, n minus n plus factorial and n plus factorial. So n minus n plus factorial is giving you n minus factorial. So this is how you get the number of microstates for this system. Let me repeat how you're finding it. You're basically saying is how many different ways you can pick n plus 1 dipoles out of n atoms. All right. So that is the way. And remember that all these dipoles are distinguishable, they're distinct. Okay, so this is the number of microstates, and obviously one can find the log of this. I have not written down the log of this expression, but one can work it out. That's not a, you have to use, again, the Stirling's formula to get an expression for that. But what is important for us is look at this. What is entropy when the system is at its lowest energy state? Okay, at the lowest energy state, all the dipoles are aligned with the magnetic field. All of them have energy minus epsilon. Okay? That is just 1 microstate, which means omega is 1 and log of 1 is 0. So entropy is 0. So entropy is 0 when all the systems are in the minus epsilon state. Okay. On the other hand, when all of them are in energy state epsilon, and energy is n times epsilon, that time also the number of possible microstates is again 1, because all of them are already in the same direction. There's no other way you can have. That's only one state. Okay? So we have this thing, situations, two extreme situations of the energy. And the one hand we have, the ground state, the lowest energy state. On the other hand, we have the state with the highest energy. For both of them, entropy is 0. In between, one can very easily check. This function is maximum when n plus is equal to n by 2. This is something we did yesterday also for the example with fluctuations. So when n plus is equal to n minus or n by 2, entropy, this omega E would be maximum. And that is the energy equal to n by 2 into epsilon. So you have this very interesting case. You can think of two extremes of the energy. At one extreme, energy is minus n times epsilon. At the other extreme, energy is n times epsilon. Both are 0. In between, when the energy is n by 2 into epsilon, entropy is the maximum. So between energy minus n by epsilon to the maximum, entropy is increasing with the energy. And then from maximum, it decreases with energy. Okay. So in the second part, the entropy is decreasing with the energy, and you will get negative temperature, because 1 by T is delta S by delta. Okay, so here we prove that way that energy would be negative. Entropy decreases when energy is greater than NE by 2. And so that is the region in which temperature will be negative. All right, so this was about how one can create, express thermodynamic properties in terms of statistical physics, and certain examples about that. The next topic which we discuss today is partition function. I don't have much time, so I have to run quickly about that. Okay. Partition function is just some function. Okay, it is expressed like this. You can take its definition. Okay. What we have here is it's a sum over all the states of the system, and for every state we are taking this factor minus beta E. Remember, beta is exponential of minus energy of the state, Rth state, divided by kT. You just take this exponential, sum it over all such things. Okay. This is a function at this point. We're writing it as a function. Okay. We're not putting actual values, we're writing just as a function. Now, a common problem remains, when you're trying to think of is what is partition function? Okay, one way is to look at it just as a definition, it's given to you. Okay. But then the question remains what it is. Okay. There you have to, in some sense, try to expand your understanding of what are the kinds of things you're dealing in physics. Okay, in the physics there are physical quantities which are directly physical, like energy, mass, wavelength. Okay, these are directly physical quantities which one can measure. Okay. But then also there are functions. Functions are not directly measurable. They may not have a direct physical correspondence with anything. For instance, a wave function of a quantum mechanical system. All physical properties of the system, they depend on the wave function. The wave function itself does not have a direct physical representation. Partition function is also something like that. It's a function made up of certain properties of the system, like the energies of different states. So it's a well-defined function. But by itself, it does not have any direct physical interpretation. Yet, it is of relevance in physics because many physical quantities, in fact, all physical quantities which have statistical physical significance, they can be mathematically expressed as functions of this partition function. For instance, the mean energy of the system is given by this. Partial derivative of log of z with beta. Beta, remember, is 1 by kT. So if you know Z, you can straight away find what is the mean energy. Pressure, the mean pressure of the system, this partial derivative. Entropy of the system, this log Z plus beta E bar. And they can be, all such relevant thermodynamic properties of the system, they can be mathematically expressed in terms of the partition function. So that is the great utility of the partition function. If you know the partition function of some system, then just by following the recipe of these expressions, we can derive expressions for the all physical properties of the system. Okay, so think of this partition function in this way. It does not have a direct physical interpretation of its own directly, but then the physical quantities can be derived in terms of this partition function. Now, there is something else. See, here we're talking about the energy states of the system. Okay, all R is basically sum over, and but so it's a sum over discrete states, the way it is written. But yesterday we discussed, for classical mechanical systems, we can represent the microstates of the system on a phase space. And every point in that phase space represents a microstate, distinct microstate of the system. Okay? So there, you're representing the states not as in terms of some discrete, a discrete set of states, but as a continuous distribution of states. Okay? So we have to do some correspondence between a continuous representation of states and a discrete representation of states. So this is the correspondence which I have written here. So what you have here is basically, this is a sum, so you're writing it as an integral over the parameters or the variables which specify different states. And what are those states? Q1, P1, Q2, P2, right up to Q3 and P3n. Remember, these are the positions and momenta coordinates for n number of particles. Okay, and each position has 3 coordinates. Each position momenta has 3 components, so that's why you get 3n. Okay, 3n position, 3n momenta. So this is then this summation will represent this integral. But then there's a problem here. Okay. This summation is basically you're adding this factor, which is a dimensionless factor. If you just take this integral is not dimensionless because Q is a distance coordinate, P is momentum coordinate. Both these are dimensional quantities. So you cannot replace a simple sum by, like this because all these now the variables here are dimensional quantities. You can't do a simple correspondence. What we do actually is we divide our phase space in what are called elementary cells. You can imagine a continuous phase space is a continuous distribution, but imagine breaking up that continuous space into small cells. Okay, we leave at this point in classical statistical physics the volume of that cell arbitrary. We just say it's small volume. We're not bothered about it as long as it's small because ultimately, okay, all the things in probability depends upon ratios. And so, whether you take the ratios of smaller volumes or bigger volumes, ultimately ratio will remain the same. So we don't worry about the exact number of volumes. So what we do, we divide the phase space into elementary cells. And elementary cell has this volume h raised to power 3n. H is coming because of a very specific reason, the symbol H, because ultimately when you go to quantum statistical physics, this H will be interpreted as Planck's constant. Not just interpreted, we can actually show it has to be a Planck's constant. Okay? That's why using the same symbol. Otherwise, this could be just some quantity, the volume of the cell, which has dimensions. So what are the dimensions of this H? H3n, H raised to power 3n is the volume of the elementary cell in the phase space. What are the dimensions of a volume in the phase space? Dimensions are basically these. Dimensions of 3n position coordinates and 3n momentum coordinates. Okay. You multiply one position with one momentum. What do you get? Angular momentum. Okay. So H by itself has the dimensions of angular momentum. Okay. And you're multiplying that by 3n. So H3n has the same volume as same dimension, sorry. It has the same dimension as Q1, Q1, P1, Q2, P2, right up to Q3 and P3n. So H3n here is the elementary cell volume in the phase class. This is a dimensional quantity. Okay, this elementary cell volume.
Dr. Sanjay?
Hello?
Yeah, Dr. Sanjay, please come closer to the laptop.
Oh, okay. The voice sound is dropping. Okay.
I mean, the trailing part is like damped oscillation. So
Okay.
the last word gets lost.
All right. H raised to power 3n is an elementary cell volume of the phase space. Okay. So what you're doing here is we have the entire volume of the phase space, you're dividing it by elementary cell volume. So basically what you're doing then is you're adding up contributions from different elementary cells of the phase space. Okay. This is the correspondence formula between summation and the continuous distribution. You have to keep it to account. Okay. Now there's another useful property of the partition function, which is this. Suppose you have a system in which the constituents don't interact with each other. They could be interacting with something external, like the example which you discussed of magnetic dipoles. These dipoles were interacting with the external magnetic field. But there's no internal interaction between these constituents. Suppose your system is made up of that in such a way, then what you can do is you can write down the total energy of the system as the sum of the energies of the constituents. Okay? So this is an example of where we're taking off still a classical system. Think of system made up of n number of particles. So position and momenta are the relevant coordinates here, which in terms of which you get the energy. Suppose there is no potential energy between the molecules. All they can do is just collide like hard balls. So then the energy of the molecule at a given moment, it's simply its kinetic energy. Okay, so energy then would be p squared by 2m. So, but what is the case is if there is no interaction between the constituents of the system, then the total energy of the system is the sum of the separate constituent energies. Okay. So this is the energy of the first constituent. Okay. 3 position coordinates, Q1, Q2, Q3, 3 momentum coordinates. So these 6 sets of coordinate, 3 position, 3 momentum, they correspond to the first particle. Okay. And similarly, there'll be second particle, and this is the position and momenta coordinates for the last particle, the nth particle. Okay. The total number of momentum position coordinates is 3n. Okay. So you have Q3n as the last, let's say the zth coordinate of the nth particle. Okay, that will be Q3n, and then the x coordinate of the nth particle, that will be Q3n minus 2, and the yth coordinate will be Q3n minus 1. So this is the set of the position and momentum coordinates of the nth particle. This is a set of position and momentum coordinate of the first particle, and all you're saying is these energies are first of all, they are functions of only the coordinates and momentum of that particle. Since there is no interaction, so energy of the first particle have no coordinates coming from the other particles. Okay, so they're separate. So this is the sum. Okay. Then remember what was the partition function? Partition function is exponential minus beta ER. E is the energy of the entire system. For a given state, you have different constituents with different energies. Okay. And the sum, of course, will give you total energy. And when you do the integral here, you have exponential. You have exponential as the argument is the sum of functions of only position and momentum coordinates of one particle. That means that we can separate out this integral into n number of integrals. Okay. That means when you're able to do that thing, then let me write it down first of all, this expression. Okay. So Z1 we call as the partition function for a single constituent or single particle. Okay. What is it? You have taken, position coordinate and momentum coordinate of the first particle, and the term which you're getting from the, if the energy is simply the sum like this, you're getting it like this. So here I've suppressed here, this P corresponds to P1, P2, P3. Q corresponds to Q1, Q2, P3. Okay. So this epsilon then is a function of P1, P1, P2, P3 and Q1, Q2, P3, and this one can do the integral. Okay. So this is then the expression for the partition function of a single particle. You similarly have the partition function of the second particle, third particle. Expression for the energy for all of them is the same, except the coordinates, their index changes. That's all. Okay. But then you integrate over them. So Z1 is same for all the constituents. Okay. Now what you can do is the partition function for the system made up of n particles, that can be written down as the product of the partition functions of all the single particles. So that gives you Z1 raised to power n. This is a very, very important relationship when you're doing numericals or problem, because often it is much easier to find this integral, okay, for a single particle than of course doing it for a 6n dimensional space. That you won't be able to do. So for systems which have non-interacting constituents, we can find the partition function for a single particle and then take it raised to power the number of particles. You get the partition function for the entire system. Okay, there is 1 by n factor, 1 by n factorial factor, and that n by n factorial factor is related to Gibbs paradox. Remember in the earlier lecture, Dr. Verma was talking to you how an entropy of mixing creates a problem for classical statistical mechanics, and that arises because in the classical statistical mechanics we overcount the number of states. We assume that particles are distinguishable while in reality they are not, and that creates a very serious problem which shows up in terms of Gibbs paradox. To avoid that, an ad hoc kind of recipe is used. Whatever you get as the number of microstates, you divide it by n factorial. Okay, so that thing then is continued over into partition function also. So this takes care of the Gibbs paradox and the overcounting of the microstates in classical mechanics. Okay, so this recipe, take it as a recipe, okay, which is valid whenever the constituents don't interact with themselves, among themselves. So ideal gas, for instance, which has no interaction between the molecules, this kind of thing will work for that. Okay, so we can write down the partition function of the entire system in terms of the partition function of the single constituents. Okay, now our time is going over, so we'll have to rush. And the next is a problem. Okay, now this is a problem, a system which is made up, you can think of it as the gas or some constituents. What you are saying is this is an extremely relativistic system. Okay? For non-relativistic system, the energy is p squared by 2m or half mv squared. For relativistic systems, the energy is momentum into speed of light. Okay? So energy of every particle is pc instead of p squared by 2m. Okay, so this is the energy of the particle, and this p is the magnitude of the momentum, which you can express as square root of the sum of the square of the constituents or the components of the momentum. Okay, so if you have a system like this with this energy of n number of particles confined to a volume v, what is its partition function? Okay, let's go strictly. So first of all, and it's assumed here there's no interaction between the particles. So one can use the recipe which we discussed just now. So we first of all find the partition function for a single molecule. We have the formula there. Energy is simply the exponential energy is minus Pc, beta times Pc. So this exponential factor is only a function of momentum. Position coordinates, very straightforward. There is no integrand doesn't have position coordinates, so we don't have to worry about this. So this integral dx dy dz, but this is over the entire volume, because every molecule, the entire volume of the gas is available to every molecule. Okay, so for this first molecule, for instance, this integral runs over the volume of the gas, and this integral simply gives you v, nothing else. Okay? Then you have this integral. Okay? Here, remember, this is the magnitude of T. So the simplest way to do this integral is to write down this kind of, volume on the momentum space. Okay, we have momentum components. So imagine, a three-dimensional space. It is not a real physical space. It's a what can be called a momentum space because its dimensions are dimensions of the momentum. Okay? So one can do radial or spherical coordinate expansion of this volume element. Okay, so this is a kind of Cartesian volume expansion. One can think of a spherical volume expansion. So that would be P square dP, then dP in terms of angles. Okay, so the angle integration will give you a factor of 4 pi, and one can do the P integration using gamma functions. You get this result. So V is coming from this first integral. Okay. And this integral basically gives you 2 divided by beta. That's all. Okay. 8 pi divided by beta. 8 pi divided by beta c cubed, essentially. So this is the partition function for one particle. Partition function for n particle is this. What is the mean energy? You take the log of this and do del by del beta. Okay. You get the result 3 n kT. Compare this with the non-relativistic gas, okay, where the energy is P square by 2m or half mv squared. There you will get mean energy equal to 3 by 2 n kT. For relativistic, you're getting 3 n kT. The system has 6 n degrees of freedom. The system has 3 n degrees of freedom. If you blindly follow the equipartition theorem, which says that every degree of freedom has 1 by 2 kT, then you would have gotten the answer of 3 by 2 n kT, but here the answer is double of that, 3 n kT. So the equipartition theorem is not applicable to this case, and the reason is very simple. Equipartition theorem is valid only on those cases where energy can be written down as a quadratic function of some variable. This is not a quadratic function. Okay, that's why we can't. So for the extreme relativistic case, the equipartition theorem is not valid. Okay. So this is the second example involving partition function. Okay. So I will end the lecture here. And before we actually end, let's take the questions. There are 11 questions at the moment here. And let me also put on the video here. Let's see. Otherwise, you'll be looking at the blank screen and some voice coming out of your computer. Why is the video not showing? All right. Why this somehow it goes away? No. Okay. Okay, there's a question about the first question I couldn't understand. Equilibrium comes under the style of Bernoulli integral form slightly that show mathematical form like this. I can't understand the question which is put by Veera Pandian Arumugam. So I can't answer that question. The second question is why you're taking K with S rather than with beta. Well, just say it convention. Okay. So it's not a, beta in fact also has, beta is 1 by kt and k is also there, okay. So remember that when you make an association, there will be some physical quantity, some physical constant playing a role. Where you put it, how you put it, that in some sense arbitrary, but once the convention begins, that just follows. Okay, so Ujjwal is asking, a system in equilibrium has maximum entropy. Okay. All right, how can you explain it physically? Okay, how can you explain it physically that why the system in equilibrium has, okay, let's put it this way, because entropy in our statistical picture is being derived from the maximum probable state, okay? So this part is clear that if you have a system of large numbers of constituents with random fluctuations, there would be a state with maximum probability, okay? Which means the system would be always around that state, okay? So imagine, you start the system far away from this state. Okay? Given the internal dynamics of the system, eventually it will settle down around the state of maximum probability. Okay? That state of maximum probability we are calling as the state of equilibrium state. Okay. Now, what do you mean by state of maximum probability? There are two things which determine the probability of a state. One, the equal a priori hypothesis, which states that every microstate has the same equal probability. The second part is that different states of the system have different number of accessible microstates. So the state with the maximum probability is the one which has maximum number of accessible microstates. Okay, this most probable state is also the state of equilibrium, because the system would eventually settle around this state, which means there will be slight fluctuations around this state. Okay. But this is a state which has the largest number of accessible microstates. And the common way of thinking is, saying that, entropy is a measure of disorder, etc. Though that claim is not exactly true, but if you think about it, if there are largest number of accessible microstates, then if you have a macrostate and you want to say something about it, there's a whole number of accessible microstates to it. Okay? That's what you say, there's a maximum amount of disorder. I put it this way, for instance, to give you the idea of disorder. Suppose, there's a dust in the room, okay? And what do you do when you clean your room, when you sweep your room? All the dust particles, which in principle could have been anywhere on the floor. So that's a state of maximum disorder, okay? When you sweep it, we bring them together to a small volume. You are decreasing the disorder. You are reducing the possible states which every dust particle can have. All right. So that way, when you collect and sweep your room, you decrease the entropy. When the dust is just settled, all the dust particles are distributed randomly, you increase the entropy. Okay. But in terms of probability, the random distribution of dust particles, that state has more number of microstates. That's why it is the most probable state of the system. That is, I think, why I would interpret, this idea how the maximum probability state is the equilibrium state that also corresponds to maximum entropy. Okay, so what you're saying, the particles who are distinguishable while taking the energy analogy sequence, although divided into n-1, which means the sticks are indistinguishable. Well, the sticks are indistinguishable because, see, when you're moving around, that's what I told you. I gave you the example earlier. Maybe I can go back to the my example there. Okay, so let me go back to the example. This is a question about this thing. Okay, how do you get these things? Okay, so what you have done is imagine these boxes here as different atoms. They are distinct. Okay, so if third atom has 3 energy packets, that is a distinct state with the first atom having 3 energy seconds. Okay, so these are 2 different things. What we can do is the interchanging of the stick is the following. You take this stick, you take these 2 sticks, okay, interchange the 2. Bring this here, bring this here. Or you can interchange this stick and this stick. Bring this stick here, take this stick here. That operation does not change the number of energy packets for the given atom. Third atom still retains 3 atoms. This atom still remains 1 atom. Okay, that's what we mean by interchanging sticks does not create a new microstate. Okay. Similarly, when you interchange these energy packets, you can take this energy packet, put it here, this energy packet, put it here. The number of energy packets still remains the same. Third atom still has 3 packets. This 5th atom still has 1 packet. So these are kind of, overcounting when when you just take m plus n minus 1 factorial. So you have to divide by these things in the denominator. Okay. So this was about the, okay, let me go to the question answer thing. Okay. About the distinguishable, the stick and the ball problem. Okay. The Cyril is asking magnetic dipole problem. It's confusing me that as the internal energy of the system increases, the temperature actually decreases. Yes, and of course it is counterintuitive. So if it is confusing, I mean, counterintuitive things, obviously they're confused. That's why they're counterintuitive. They're unexpected. Okay? But I would advise you to follow the logic. Okay? Don't just have some fundamental assumption in your mind that temperature can never be negative. Okay? Temperature is a derived property. So you have whatever, then follows, it's a derived property, means it's a derived property of the relationship between entropy and energy. Okay? And we have the example of the system where if there's an upper bound on the energy, okay, then if energy goes beyond a limit, if you increase the energy, entropy decreases. Temperature is negative. So think of this way, temperature as a derived quantity. Okay? Now the interesting question is that, are systems like this physically possible? And the answer is yes. You can create systems which can have negative temperature. Okay? And there's a whole lot of physics around this, for how long they can be sustained. Such systems cannot be sustained for long. They're unstable. Okay? And through random distribution fluctuations, they again go back to systems of positive temperature. But nevertheless, such systems are physically possible. So that's the idea of, I would suggest, don't take temperature as a fundamental quantity which has to have positive value. Think of it as a derived property of statistical systems, and then you follow through what happens to it. Okay, what is the difference? Veerapandian is asking, what's the difference between partition function, statistical mechanics, and discrete system of quantum mechanics? How they will differ? Well, quantum systems also have partition function, and the basic definition remains the same. It's basically sum over exponential of minus beta ER. The definition remains same. How you evaluate it, the expression for the partition functions, that obviously is different in classical system versus quantum systems. Okay, so what is a state? The Mishab is asking, what is a state? Okay, because the partition function has, a state over, we said sum over all the states of the system. Okay. This is basically, see, think of this. Your system is in some macro state. Okay. For instance, this system could be in contact with the heat reservoir at temperature T. So you'll say system, the temperature of the T is, temperature of the system is T. It has some volume, okay? It has some number of particles. It has some pressure. So all these parameters will define a macro state of the system. Now, when for the partition function, we say sum over all the states, our idea is that we sum over all the micro states of the system. Got it? Okay. So that sums is over all distinct micro states of the system. All distinct accessible micro states, because if you have, there's corresponding to macroscopic parameters, there would be some limitations put on the possible micro states which are accessible to that micro state. Okay. For instance, for the example of the cylinder, we saw that, the position coordinates, they were limited within a volume. Okay, so there could be some constraints. So all the accessible microstates, so that sum extends over all the accessible microstates. Samiran is asking, when we talk about the entropy of a thermodynamically interacting system, we generally talk about the change in entropy, as it is not possible to determine it exactly. If I'm right, then can we understand that the Boltzmann relation gives the exact entropy of system? Okay, from thermodynamics, yes, we do talk about the change in entropy. But remember, when you include the third law of thermodynamics, and one of the states in the third law is entropy is zero at T equal to 0. There again, you know, we can begin to talk absolutely of the entropy. Okay? So right up to second law of thermodynamics, it's only the change in entropy. Okay, but with thermodynamics and statistical physics, we can begin to talk about absolute value of the entropy. But remember, in statistical physics also, it's k log omega. The minimum value for omega is 0. A minimum value of omega is 1 because system has to have some at least microstate. You can't say system has 0 microstate. It means system does not exist. Okay? So minimum number of value of omega is 1. So minimum entropy is 0. And then whenever, you know, whatever number of value of omega, it will always be some positive natural number. It's number of microstates. So 1, 2, 3, 4, etc. It will be a natural number. Log of natural number would be positive. Okay? So entropy then from that definition is positive constant. Okay, so the question is, you know, when in the elementary cell, we wrote it in terms of quantum system, and above numerator is a classical system. How do you do it? See, I would advise you at this point, take H, though the symbol is of course eventually goes down to the Planck's constant, but in classical physics, we just take it something. Okay? It's not Planck's constant. It is just some constant, it is just some volume in the phase space, which has the same dimension as Planck's constant, but that's subsidiary to our consideration. We divide the phase space into elementary cell, and we say one elementary cell has the volume h3 raised to power 3n. That's it. Okay. Ultimately, okay, H would not. Okay, H appears, of course, in partition function. Okay, and it will appear in other things also. But remember, the physical quantities, entropy, energy, etc., they were all of them were partial derivatives of the log of the partition function. Okay? So ultimately, when you do those things, H does not appear in them. So as far as the physical properties is concerned, what is the volume of the elementary cell has no effect. All you need is that this elementary cell should be small compared to the dimensions of the system. That's all you need. Ultimately, the volume of the cell would not show up in your final results because you're taking, for all physical quantities, typically you have the log of Z and then the partial derivative, and the constant parts then drop out. So the actual value of L does not have any physical consequence in the classical physics. Of course, when you go to quantum physics, then H does play a role. But that's not what we're discussing. So how does we connect beta and temperature connectivity? Is it experimental? No. See, we connected, we looked at the two expressions. One was, 1 by omega del by del, what was that? Del by del E of log omega, okay? What we said is that the statistical picture, this function of the statistical system should have the same value for two of them. We call that beta. All right. Now we know right away that beta has to be something related to temperature, because in thermodynamics, you say that when the two systems are in thermal equilibrium, they have the same temperature. Now, why we're saying is 1 by T rather than T or some other function of T, because if you look at, you're making an association between different expressions. So one expression was the one, okay, let me go back to explain that. There were two expressions. Okay, so this is one expression, del by del of E. Okay, look at this, del by del of E of log of. That is equal to beta, okay? On the other expression, we have the similar form of the expression, del by del E. And that is equal to 1 by T. Okay? So the mathematical form of the expression is same. Okay? And so that way we can compare the two. Okay? The other expression is also the same, similar mathematical form, del by del E of something, call it S, equal to something else. So this side we take as beta, And here we have log of capital omega. That we take as S. Okay. Now the other question was why we're putting K with S. That's an interesting question. And the value of K, of course, see, either you can, when you begin to compare with experimental values, that gives you what will be the value of K and what will be the multiplicative factor. Okay. The course, so I'll leave it at that. Okay. But the comparison was not with the experiment when you interpreted beta as 1 by kt and SSK log omega. Interpretation was through comparison of two mathematical expressions, because the mathematical operation in the two expressions was same. It was del by del E of something equal to a constant. That's how it worked. All right. So let's see if there are any more questions. Oh.
I think it's too long, Dr. Sanjay. Maybe one or two that's left. We can deal with it later.
Yeah.
I think you've already reached the end. One or two questions are there. You can probably answer.
Two questions are. I will just say that m plus n minus 1 factor. I will put my PDF of the lecture note also, so that will be, you will have more better explanation.
Yeah, and yes, and Dr. Sanjay, they have to read the books simultaneously.
Yes.
If they have questions like, please explain m plus n minus 1 factorial, then that means your base requires a little bit revision.
Right.
It's not a problem. I mean, you can do it in a week. It's not a problem. Everything is being provided to you. Just go through all this.
Yes.
Amber
is asking about why we take the momentum limit to infinity. It does not violate the special theory of relativity. Okay. Momentum can be infinite also in special theory of relativity, so that does not violate special theory of relativity. Okay. But your name Amber Hastinapuri is interesting. Hastinapur, of course, as you know, is an old town associated with the Mahabharata. So I find your name very interesting here, Amber. So these are the questions, and I guess we come to the end of the presentation.
Yes.
Thanks to all the participants. Thanks to Dr. Verma, Dr. Bindal, and Nasi. And I hope
Thank you, sir. Thank you so much.
Thank you so much, Dr. Sanjay. If in the future you feel like taking any more classes with the students, you are most welcome. It's up to you.
Yeah,
we can
let's
have
see.
some more numericals. Yeah, it's all, we are welcoming everybody. The students are liking the lectures. And actually, any person who is sincerely learning and reading simultaneously can really gain a lot. Because in most of the, even YouTube lectures, one doesn't go so deep. And in every nook and corner, why is each factor coming in and so on. Although there are beautiful lectures and NPTEL, students can look at NPTEL lectures also, EPG Pathshala lectures also, and there are hundreds of others. I'm providing them a list of all YouTube lectures of statistical mechanics. We are also simple physicists, and there is no claim that what we say is only the best. Not at all. No teacher will say this in physics, at least. That my lecture is the ultimate.
Following good textbooks, and I will strongly advise for the parts which I have done. Patharia first chapter is very good. Please go through it.
Yes.
And interesting problems, which you can try on your own.
Definitely. Okay, then with this we end this very long session. Thank you, Dr. Sanjay.
Thank you, Dr. Verma.
Thank you, sir. Dr. Sanjay.
And
Ms. Varsha, please stop the recording now. No, first of all, please display the slide. Dr. Sanjay, please stop sharing.
Yes, I will.
Ms. Varsha, please, the last slide for tomorrow.
Yes, ma'am. I'll be sharing it once sir is.
Yeah, I've stopped my sharing now.
Yeah, it's okay.
Stop the.
Tomorrow we are continuing with statistical mechanics, and you'll have a lecture by Dr. Aditya Saxena, and you'll have a lecture by me, and you will have a lecture by Dr. Shyam from Kirorimal College. So you have a number of teachers teaching you the same subject, I'm sure. With each student whose brain level, understanding, everything is different, this combination in all together will be beneficial to you. Okay, then please, Ms. Varsha, please